This video will present an article on the Hansen problem, or its solution via geometric algebra. And the Hansen problem is a classic one from surveying, from plane surveying, although it can also be extended to 3 dimensions and even above. In the Hansen problem, we are trying to determine the locations of 2 unknown points with respect to 2 known points by measuring angles as seen from the unknown points between the 2 knowns and one of the knowns and the other unknown. So, as the article mentions here, they're revisiting the Hansen problem, which means they're going over the classical solutions via trigonometry and other methods. And one of the things that I think is really enjoyable is to see the original solution to this from the Proceedings of the Royal Society, written on the old, or written in Old English on this yellowing, on these yellowing pages here. So that was kind of fun. Back to the recently published article. It begins with an abstract, of course, and an introduction, and background and literature review, including the Collins solution that I showed a moment ago. And then it goes into the solutions via classical trigonometry. Here's a diagram. And also by complex numbers. The solution by classical trigonometry is quite ingenious and insightful. The only thing is it becomes quite complex, and as a result it's quite prone to error propagation, which means that small errors in the measured angles turn into big errors in the estimated positions of the 2 unknowns. After presenting the trigonometric solution, the authors present a solution via complex numbers, which I thought was quite wonderful. So I won't go through that in detail. You can check it out in the references to the paper, but I really recommend it. I quite liked it. Then comes a solution via vector geometric algebra. Vector geometric algebra is the plain vanilla Euclidean version that I myself am familiar with. So there's a brief introduction to VGA, and then we get into the solution. And the thing that I liked best about the VGA solution is, as we note here, it's a solution that is actually both intuitive and straightforward enough to be discovered by a high school student who knows the fundamentals of VGA and has had experience in other classes with translating, rotating, and scaling figures. So there's nothing really difficult about this solution. It would be, I think, quite accessible to a high school student who could have come up with it him or herself. After presenting that solution, there's a couple iterations here of going through an original figure and then kind of polishing it to come up with the version that the authors really wanted to use here. After that vector geometric algebra solution, the authors present the solution via conformal geometric algebra, which is quite a powerful tool, and as I note, it's really overpowered for a 2-dimensional problem. But the reason for including it in this paper is that CGA is quite a powerful tool for higher dimensions, and here the reader can get an idea of what it's about. Also, CGA allows the user to work directly with figures, manipulating those, instead of having to translate things into sines and cosines and such. After presenting that solution, which is a bit involved, I admit, the CGA solution actually translates an older, well, in fact, Collins solution which we saw earlier, into computable elements via CGA. So that's the tie-in there. I should have mentioned that earlier. Now, after presenting that solution, the authors did something that's quite important and that the reviewers were happy with originally, and or with the amount that had been done, but also asked for more about the analysis of execution times and such. So here is a comparison of execution times for the vector geometric algebra, complex number, classical trigonometric, and conformal geometric algebra solutions. Then one of the things that the principal authors did that was very important was a characterization of error propagation within or for each method. Now, each of these figures, it would take some explaining, you'd have to read the text, but if you look at the original or the problem itself here, you might understand that if your unknowns are in certain positions, for example, if one of your unknowns is squarely between the two knowns, you could get in a situation there where small errors in your angle measurements might blow up into big errors in your estimated positions. So that is something that was important to assess, and the authors came up with a way of doing that and of displaying it via these diagrams. So there's a little bit more in this article about kind of error tracking or a characterization of error propagation. And after that, as usual, it ends with conclusions. So I hope that this may interest you and that you'll check out the article, which again I will link in the video description. And I hope that you'll consider joining our LinkedIn group, Pre-University Geometric Algebra. And I'll also link that group in the video description. Thank you for your time.